function standard 1. We're still in just looking at what is a function. So we're looking at representing functions. The learning target this time is that we can look at those graphs and those tables and those equations, and we can determine if they are a linear or a nonlinear function. So going back to LT1, I gave you examples of what makes a table, a graph, a context, an equation a function or not a function. Well, learning target 2 takes it a step further. We're just going to look at, so if we were to do like a graphic organizer here, so we have function and non-function. Well, functions break down into different types. So the type we're going to look at in particular in 8th grade math is called the linear function. Okay, so functions can be linear, and then when you get into algebra, you'll look at quadratics and cubic functions and exponential functions. But in 8th grade math, we really focus on looking at the idea of a function and then really look at this name of this function called a linear function. So that's what learning target 2 is all about, is when we look at these graphs in our tables and our equations, how do we know they're this special type of function known as the linear functions? So to start with, we're just going to look at 3 characteristics that make a function linear. So first of all, when you're looking at a linear function, you will notice it will make a straight line when it's graphed. When you're looking at a table, it's going to show a constant rate of change throughout the entire table. And when you're looking at an equation in linear function format, it will be written as y equals mx plus b. Now, on the contrast of that, so how do we know if it's not linear? Still a function, but not a linear function. It's one of those other ones that I named, plus there's more. If it's not a linear function when graphed, it is not a straight line. When it's not a linear function, the rate of change is not constant. And when it is not a linear function, it is not written in the format of y equals mx plus b. So let's look at some examples. We're going to start with just graphs. So which of these graphs represent a linear graph? Well, the first one, remember if you go back, I told you to be a linear function, the graph is going to be a straight line. I see a line, it's very straight, so I can say this is a linear function. If I go back to the idea of function, if we did the vertical line test, we would notice that every time I made a vertical line, it would only hit the graph once. This one right here, okay, it is not linear. This is not a straight line, it's a curve. So this is nonlinear. If we go back to the idea as a function or not, if I take a vertical line test, it actually will pass the vertical line test. So it's just known as a nonlinear function. And then as you get into algebra 2 or 1, you will notice that that is a quadratic function. Looking at this next graph, okay, it is a straight line, okay, but I don't want this to trick you. Notice this straight line. If we did a vertical line, it's going to hit infinite amount of times. So it is not even a function. Because it's not a function, then you can't name it as a linear function. So if you go back to here, where I started, this is a non-function to start with, so it can't even go into the category of linear, because linear only is under functions. So this is not even a function. And the last one here, it's a straight line. So it could be linear. Do the function test. It is a function. So this one is a linear because it's a straight line function. Okay. So there's some graph examples about the difference between function and non-function and linear and nonlinear. Let's look at some tables here. So an example of a non-linear table. So if we look at the difference of values in the y's, so we're going to notice that increases by 10, this one increases by 20, this one increases by 40, and this values increase by 80. So again, I figure that out as 10 to 20 is an increasement of 10, 20 up to 40 is an increasement of 20, 40 up to 80 is an increasement of 80, and then 80 up to 160 is an increasement of 80. Now, if we look at the x's, because you got to look at both sides to see if there is a constant rate of change. This is 0 to 1 is 1, 1 to 2 is adding 1, 1 to 3 is adding 1, 3 to 4 is adding 1. So there's a constant rate of change on the x side, but there is not a constant rate of change. And let me make sure you understand constant rate of change. That means you're adding or subtracting the same number every single time. Again, to be constant, you are adding or subtracting the same number every single time. Now, if you look at this, there's definitely a pattern. Add 10, 20, 40, 80, but this is not constant. If it was constant, it would have been 10, and then plus 10, plus 10, plus 10. Here is an example of a linear. So to go from 10 up to 20, your rate of change is 10. 10 to 30, your rate of change is 10. 30 to 50, your rate of change is 20. And then 50 to 80, your rate of change is 30. Now, if we look at the x's, you're going to add 1. 1 to 2 is add 1. 2 to 4 is add 2. And 4 to 7, you add 3. So if we look at the rate of change, that would be the y and then the x. So if we look at like an actual rate, let's put it fractionalized, and you actually put the y's on top. So you're changing 10 to 1x. So the y's, this is the symbol for change. Change of the y was 10. The change of the x was 1. Okay, we can see that's the same for the second one. If we look at this one, so the change of the y was 20. The change of the x was 2. Well, 20 over 2 is the same thing as above 10. 10 over 1. Okay, if we look at this last one, okay, the change of the y over the change of the x. So the change of the y was 30. The change of the x is 3, and that also is 10 over 1. So if we go back to the definition, to be linear, it has to show a constant rate of change throughout the whole table. That doesn't mean that it's always going to be adding or subtracting the exact same amount in the table. That's what constant rate of change, it has to be the same rate, but you might have to really look at those rates and make sure that when you do the change of the y, how the change of the y's over the change of the x's, if you look at those values, do they reduce to that same amount? So in this case, again, it was changing 10 y's to every 1 x. Over here, if I just go back, this is the change of 10 to 1. This one's a change of 20 to 1. So right away, I can tell that this is not going to be the same constant rate. Okay. So let's look at some tables. Let's kind of break them down and see what we got here. So change of the y. So 7 to 4 is a negative 3. 4 to 1 is you're subtracting 3. 1 to negative 2, you're subtracting 3. And negative 2 to negative 5, you're subtracting 3. We'll look at the x's. Negative 2 to negative 1 is you're adding 1. Negative 1 to 0, you're adding 1. 0 to 1, you're adding 1. 1 to 2, you're adding 1. So our rate of changes, the y's, change of the y's are going down by 3 as the change of the x's are increasing by 1. So that is definitely a rate of change that is constant. So this is a linear function. Okay, next one here. The y's are changing. 6 to 3 would be subtracting 3. 3 to 2 would be subtracting 1. 2 to 3 would be adding 1. 3 to 6 would be adding 3. Over here, looks like the exact same pattern as the previous one. We're just adding 1 every single time we go up. So if we look at these rates of change, so I have the change of, you're going down by 3 on the y, change of the x is going up by 1. Check the second one right away. I notice that the y's are going down by 1 and the x's are increasing by 1. Well, right away I can see that is not a constant rate of change. Now, check if it's a function or not. Well, if we look at every x, it has its own y value, even though this -2 has an output of 6 and this 2 has an output of 6. It doesn't mean it's not a function. It just, every x value has its own. So this is a function. It's just not a linear function. And the last one here, this one they just want us to put in the points. So this is -10. The y would be 10. X is -5. The y is 4. 0 is the x, y is 2, 5 is the x, y is 0. So if we check our rates of change here, so 10 to 4 is going down by 6, 4 to 2 is going down by 2, 2 to 0 is also going down by 2. Check their x value changes, are known as the rates of change. -10 to -5 is increasing by 5. -5 to 0 is also increasing by 5, and 0 to 5 is also increasing by 5. So if we check the change of the y on this first one, -6 over change of the x is 5. So our rate of change is -6 to 5. And then if we check the next one, change of the y on the next one, actually the next two, is -2, and the change of the x is 5. Well, those two rates of change are not the same. Now, is it a function? It sure looks like it. Every x value has its own y value. So it's a function, just not a linear function. So the only linear function we have on this one was our first example. Okay, last part we're going to talk about is equations. So what form are linear equations written in, linear function equations written in? They are all written in y equals mx plus b. Now at this point it looks pretty foreign. We will be studying y equals mxb a lot. Just right now, just recognize what format it's in. So y is always a y. We'll do a couple examples here. M actually stands for slope, how steep a line is. Let's say our slope is 2. Okay, x is always an x. So the y and the x don't change. And then b is known as the y-intercept. It's where the line crosses the y-axis. So let's say it crosses at 5. So the format is, again, y equals mx plus b. In my case, I made equation y equals 2x plus 5. Okay, we can do another one. Y equals, you got to put a number in for the slope. So let's say the slope's going down 1/4. And put in your x, and then let's say your y-intercept is at 10. So it's crossing at -10. And I could sit here all day long and come up with equations. You just have to put a slope in. It doesn't matter if it's a positive slope, if the line's increasing, or if it's a negative slope, the line is decreasing. Just put a number in there. It can be whole numbers, it can be fractions, it can be decimals. You can go 1.5x, and then whatever your value you want for your y-intercept, or where it's crossing the y-intercept. So we can say that's like 1/4. Okay, so just recognize at this point that all linear functions are written as y equals mx plus b. Some examples of when they're not written as y equals mx plus b, but they're still functions, when there's exponents. So notice on the equation that we have done, y equals mx plus b, there are no exponents higher than 1. So here's an example of an exponent equation that's not linear. It's still function, but not linear. So let's go y equals x squared plus 2. Okay, this exponent throws it off. Okay, look at the difference. We have y equals mx plus b. Okay, notice that x is just one single x. If I want to put an exponent on, I could technically put a 1 there, but we don't. Can have an exponent here. Or let's say y equals x cubed minus 5. Again, no exponents higher than 1. So if you see an exponent of 2, 4, 7, 130, you know that that is not a linear function because it's not y equals mx plus b. No square roots or cube roots. So nonlinear would have no square or cube roots. So for example, y equals the square root of x. Still a function, but definitely not a linear function. Or we could do the same thing, y equals the cube root of x. So there will be no exponents, there'll be no cube roots, no square roots. And then the last one, no more than 2 variables. And normally those 2 variables are x and y. So they are not going to be linear if there are more than the 2 variables. Normally we pick x and y. So for example, if we had an equation that said 2x, we'll put y equals 2x plus 3z plus 10. This is definitely not a linear function. Way too many variables, so we have 3 variables. Again, linear functions are written in y equals mx plus b.